Okay, so we're going to look at another example of local extreme values. Now with this function that looks very, very weird. It looks like a polynomial, but then we add an e to the x, which makes things a lot more weirder. And the only way to do that is by the first derivative test. And I took this from the previous video. This is the same exact graphic that I used, or I drew. The first derivative test says if we can find critical points, which are where the first derivative is 0 or undefined, in other words, the tangent line is 0 or it's undefined, we can find maxes and minimums very easily by applying the first derivative test. In other words, if we notice that this part on the left of this critical point is positive, and then on the right hand side it's negative, it has to basically be a maximum value, hence the local max. And then minus to plus is local min, and then there are cases where there's neither, and I'll show you another example. This is a minus, 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 all the way from the left and the right side of this graph. So now we apply it to this one. The first step is always take the first derivative. And now, let's see, how do you find the first derivative? We have to use the product rule. So I'm going to use the product rule right here. So this is the first one, this is the second one, and I'm going to do it without the table that I typically use. So this is 2x e to the x plus x squared minus 3, that. So we have the formula for the derivative, and now we want to find the critical points, and in order to find the critical points we need to set it equal to 0. So set this equal to 0. And now this is the difficult process of finding where this is equal to 0, or finding the zeros. Okay, how do I do this? Well, first off I could factor out an e to the x because I notice that that's a common factor. And I'm going to rewrite it in this way. Maybe you'll see exactly where I'm headed towards. I can factor this out. So e to the x, what is it going to be? So minus 3 minus 1. So it's x plus 3, x minus 1. That seems like it's the one. And then I just solve for x, right? 1 is this 0. It's never 0, so it's never going to have a value where it's 0. This can be 0 at x equals minus 3. And then this one's x equals 1. Okay, we found the critical points. And now we go on this process of finding which regions are positive and negative. So we separate it into 3 regions with this critical point. And since it behaves like this in this function, we know that there's not going to be another critical point to the left or right. In other words, it's all going to have the same behavior in these regions. And by behavior, I mean positive in this region or negative in this region, no matter what. It's never going to be positive, 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 and somewhere in here, negative, because we already found the critical points. And if it changes from positive to negative, that means we missed a critical point somewhere in between. And then with that, we use the fact from the first derivative test where if it changes sign, it's either positive or max or a min, or neither, depending on what the sign is. So we take a couple test points. I want to take 0. 0 is always easy to plug in. 2 is easy to plug in. And let's just go negative 4. So this is the test. So let me scroll to the right. So test which points? I want to do 0, the derivative at 0, the derivative at 2, and the derivative at negative 4. And at 0, where is the formula for the derivative? It's right here. Oops, I forgot to notate that. So it's right here, so that's what I'm going to use. 0 plus, so 0 plus 0 minus 3, minus 3 e to 0. This is a minus. That's all I care about. I don't really care too much about the actual value. I just care about the sign. So the more work you do, the less work you do, the better, right? So I just care about sign. So now we plug in 2. Let's see, if I plug in 2, I can use a calculator. If they give you a calculator, you can just plug in 2 to here and see what you get. Let's see, 4 times e squared, and then plus, let's see, plug in 2, you get 4 minus 3 e. In other words, e squared, which is equal to a positive value, right? 5e squared. And then negative 4, this is negative 8e to the minus 4. And then plus, let's see, 16 minus 3, that's 13e to the minus 4. In other words, it's positive because it's just combining like terms. You get 5e to the negative 4, which is positive. So, in other words, we have it separated into three regions. A minus region here in the middle, and then plus regions here. That means we know that there's going to be, if this is a positive to a negative, and then a negative to a positive, this is going to be a local max. And this is going to be a local min. In other words, there is at x equals negative 3 is, let me write it more grammatically correct, x equals 3 is a local max, and then x equals 1 is a local min, using the first derivative test, and we are done. So, see the power of the first derivative test allows us to find maxes and mins of functions very easily, just by taking the derivative and knowing what signs they are based on the critical points. And that's the end of this video, or this example.